In order for a function to be continuous at a certain point x equals c, three things have to be true. First, f of c must be defined. Second, the limit of f of x as x approaches c must exist, or the limit from either side as x approaches c must exist. And lastly, that f of c is equal to the limit of f of x as x approaches c. So let's try applying these three things here to these graphs. So first of all, let's see, is f of c defined? So in this case, f of c in this case is 1. In this case, there's actually a vertical asymptote here, so it actually is undefined. Second, that the limit of f of x as x approaches c exists. So in this case, from the left, it approaches negative infinity, and from the right, it approaches positive infinity. So actually, in this case, the limit does not exist. And because f of 1 is undefined, the limit does not exist, we don't really have to worry about that last one. So let's go on to the second one at this point. First is f of c, or is f of 0 defined? In this case, it is. There is a kind of point plotted here for when x is equal to 0, and that point is at x2, so f of 0 is defined. 2. The limit as x approaches 0 of f of x. It doesn't exist? Yes, because from the left it approaches 0 and from the right it approaches 0. So in this case, the limit is 0. Lastly, is f of 0 equal to the limit as x approaches 0, x. In this case, they actually are not equal because 1 can see here, 2 and 0 are not equal. So in this case, there is actually a discontinuity at this point. So the first example we're going to be looking at for proving continuity is f of x is equal to quantity x minus 1 squared plus 2. The first step we have to take when it comes to proving continuity is proving that f of c, in this case f of 2, is defined. So does f of 2 have an output? And when you plug back into the function, you would find that f of 2 actually does have an output of 3. The second step that you have to take when it comes to proving continuity is proving that the limit of f of x as x approaches 2 from the left is equal to the limit of f of x as x approaches 2 from the right. So first of all, what we're going to try to do first is find what these limits are. So again, you can plug back into the function to find these limits, or you can do this graphically. There are a variety of methods that you can use. Nonetheless, once you find the limits, you would find that both of these limits are equal to 3. So because the limit from the left and from the right are equal to 3, we can state that the limit of f of x as x approaches 2 is equal to 3. The last step we have to work on when it comes to proving continuity is proving that f of c, or in this case f of 2, is equal to the limit of f of x as x approaches 2. So when we look at what we've already determined, we can see that f of 2 is equal to 3, and we can see that the limit of f of x as x approaches 2 is also equal to 3, meaning that f of 2 is equal to the limit of f of x as x approaches 2. This basically means that f of x is in fact continuous when x is equal to 2. So the next example we're going to be looking at is this piecewise function, and in particular we're going to be seeing if this piecewise function is continuous when x is equal to negative 2. So the first thing you have to really deal with when proving continuity is it defined at that point, so is f of negative 2 defined? And in this case it is. You can actually plug this back into the function and find that f of negative 2 is equal to just 1. The second thing we have to prove is that the limit of f of x as x approaches negative 2 exists, or that the limit from either side are equal to each other. So let's start off with the limit of f of x as x approaches negative 2 to the left. So if we plug this back into the function, or you could just look at this graphically, but you would find that the limit of f of x as x approaches negative 2 from the left is equal to negative 1. We're going to do the same thing from the right, so the limit of f of x as x approaches negative 2 from the right. Again, plug it back into the function, or just look at this graphically, and you will find out that the limit from the right is actually equal to positive 1. Seeing that the limit from either side are not actually equal, we can state that the limit of f of x as x approaches negative 2 does not exist. At this point, you wouldn't really need to do any more because we know for sure that f of x is not continuous at x equals negative 2, but just to, make sure it gets across. The third thing in general you'd have to prove is that f of negative 2 is equal to the limit as x approaches negative 2. Basically saying that since the limit of f of x as x approaches negative 2, because it does not exist, we can deduce that f of x is not continuous at x equals negative 2.
Now that you've learned how to verify that a function is continuous, we'll introduce you to discontinuities. So, what's a discontinuity? Any point at which a function fails to be continuous is called a discontinuity. There are various types. As per the first graph, a function f has a removable discontinuity at x equals a if the limit of f of x as x approaches a exists, but either f of a doesn't exist or the value of f of a is not equal to the limiting value. If the limit exists but f of a doesn't, then we might visualize the graph of f as having a hole at x equals a. If we remove the hole, the function would be continuous, hence the term of this function being a removable discontinuity. A jump discontinuity appears when the left and right values at a point x equals a for a limit do not match each other. In some functions, the values of the function approach positive infinity or negative infinity as x approaches some finite number a. In this case, we say that the function has an infinite discontinuity or a vertical asymptote at x equals a. The next topic is differentiability. For a function to be differentiable means that the derivative exists. If f of x is differentiable at x equals c, then the limit as x approaches c of f of x minus f of c over x minus c must exist, meaning that the limit as x approaches c from the left and the right must equal each other. Furthermore, if a function is differentiable, it must be continuous. However, a function can be continuous and not differentiable. The first function we have is x squared plus 2 at a point c equals 2. Incorporating the definition of differentiability, we get the limit as x approaches 2 of f of x minus f of 2 over x minus 2. When you plug the function in as f of x and plug in 2 into the function, you get the limit as x approaches 2 of x squared plus 2 minus 6 over x minus 2. This all simplifies to the limit as x approaches 2 of x squared minus 4 over x minus 2. You can then factor x squared minus 4 into x minus 2 times x plus 2. And the x minus 2 in the numerator and the denominator simplify to 1. You are left with just the limit as x approaches 2 of x plus 2. When you plug in the point c equals 2 into x plus 2, you get 4. Therefore, because the limit as x approaches 2 of f of x minus f of 2 over x minus 2 exists, f of x is differentiable at x equals 2. In this next example, we have the function x to the 2/3. Again, using the definition of differentiability, you get the limit as x approaches 0 of f of x minus f of 0 over x minus 0. When you plug in 0 into x to the 2/3, this simplifies to just the limit as x approaches 0 of f of x over x. When you plug in x to the 2/3 as f of x, you get the limit as x approaches 0 of x to the 2/3 over x. Simplifying this equation, you get the limit as x approaches 0 of 1 over the cube root of x. If you plug in 0, you'll see that the limit as x approaches 0 does not exist. Therefore, because the limit as x approaches 0 of f of x minus f of 0 over x minus 0 doesn't exist, f of x is not differentiable at x equals 0. This last problem will incorporate both continuity and differentiability. We have the piecewise function f of x, and the problem states that if f of x is continuous and differentiable for all values of x, what are the values of a and b? If a function is continuous, we know that the limit as x approaches a point from the left and the right have to equal each other. As the function shows, we can write the point as c equals 1 and plug in 1 to the two parts of the piecewise function. We see that from the left, the limit as x approaches 1 equals to 3 minus 1, or 2. Therefore, the limit as x approaches 1 from the right has to equal to 2 as well. When we plug in x equals 1 to ax squared plus bx, it simplifies to a plus b, and we know that a plus b has to equal 2. Next, using the definition of differentiability, we set the left and right limit as x approaches 1 equal to each other, plugging in the respective functions of the piecewise and simplifying. You eventually get that negative 1 equals 2a plus b. Now we have a system of equations. From a plus b equals 2, we can isolate b and get b equals 2 minus a, and plug in b to negative 1 equals 2a plus b. You'll find that a equals negative 3. Using simple algebra and repeating these steps to find b, you'll see that b equals 5. Therefore, to make this function continuous and differentiable, a equals negative 3 and b equals 5.